next important topic is independent random variables. I want to conceptually consider two different situations here. The one is the most straightforward construction where you know that you have two independent experiments, right. X is defined on that is there when you start off, you are already coming with this information that we have two independent experiments, x is defined on one and y is defined on the other, any two random variables that defined that way, right. No restriction on what x and y should be, but there this could, I do not think I need to explain this any further, right. You can even consider two independent tosses of a coin or two independent rolls of a die as two different experiments in this, for this case, right. Okay. How do I, in this case, can I construct a joint PMF of x and y? Answer is yes, obviously, right. So i.e. we have PMF of x, of course this is this individual PMF is Px, and for y is Py. Even though I put dots here, of course I have omega x, so I have an omega x here and I have omega y here also, right. The set of values that x can vary over and y can vary over. So now if I consider the combined experiment, right, which is doing both experiments together, I get the combined space omega xy is what? By combining the two experiments we get so that gives you omega xy must be what? Always omega x cross omega y, because in this case the one experiment does not in any way constrain the other one because they are independent. So omega xy must be omega x cross omega y. So you have a nice rectangular grid of points in omega xy. Remember this is where we are earlier we had what did we call it, omega 1 cross omega 2 or something. When I first introduced composite experiments many classes ago, we had some similar notation, right. The first time we talked about it we used omega 1 cross omega 2, if I remember right, or I think so, right. But here we are specifically looking at just combining these two random variables, that is all. We are not interested in combining the experiments at a more abstract level. So if you look jointly at the values taken by the pair xy, they must take values only in this omega xy, and that is all we are concerned about here. So what is the joint probability here? Just going back to intuition, what do you think? So this joint probability Px comma Pxy xy, this joint probability, which is basically nothing but Px equal to x. Remember this joint probability is always the intersection or a joint event x equal to x, y equal to y. And now we are going to draw upon the fact that the two experiments are independent. So the event x equal to x must be independent of the event y equal to y because the experiments are independent for every small x and every small y. So this is the most fundamental equality that characterizes independent random variables. That is, here we are actually going from the marginal to the what? To the joint. So in the independent case you can go from You can always construct the joint as a product of the marginals. This is doable, is fine. The marginal PMFs and the joint PMF. So why do I get this once again? Because this equality comes because x equal to x, again I write it because this is important, are independent events. Not just for some x and some y, for all points x, y, like in omega x, y of course, which is obvious. This is the only, this is the most popular or the most commonly encountered situation, right? We always combine independent random variables to form bigger spaces, or independent experiments to form a bigger composite experiment. Supposing you find that you define two random variables x and y such that your omega xy first of all is a nice grid, and secondly you find that the joint PMF you calculate it and you find that it is in fact the product of the marginals. This is the situation that we had first when I talked about independence of events, right. So magically some PAB happened to be PA times P of B. Like that you can also get PXY, this equality can hold even without explicitly being forced. In other words, you have the same mathematics whether by whatever means, whether you are forcing it or it just happens by itself. In either case it does not matter, x and y are said to be independent random variables, right. So either they are independent by construction or they are independent somehow by, so you do not care how they become independent. So sometimes it turns out that x and y can be independent just by accident, just like the independence A and B of events A and B. And we will look at some examples of this in the homework, in problem set 3. Instead, if you do not like the word accident, you can say by coincidence or whatever. You can use a different way to say it. So this is independence by construction. I can add it here. So what happens here? Same condition, namely Pxy equal to Px Py. I am not writing the arguments because I have already written it out here. Main thing is that condition should hold for all points in omega xy. The maths is the same. How you get it is different. Okay. Let me put it here, can also be, but it is right, it is useful to note this, right, that you can get it when you when it doesn't, it's not so obvious. Anyway, we will come to, this is best taken up in a problem, in a homework problem and not here. So I leave it, I just make the statement and leave it like that. Now independent random variables, it turns out, right, are the one of the most useful things that we have, because we will see later on how you can combine more than two. You can combine, in fact, a countable number of them. You can combine some finite number of them you have, right. Okay, so maybe I should talk about this. So when x and y have the same PMF and are independent, what do you call them? Supposing x and y are independent random variables, that means that essentially this is satisfied no matter how, and it turns out px, right, the function px is equal to function py. What do you call them, x and y? They are called IID. This very important moniker, if that is the word I am looking for. IID stands for what? Independent and identically distributed. And clearly, if you have n identical repetitions of an experiment, you can define, if you say xi is some random variable on the ith experiment, then you have n independent IID random variables. And these kinds of things are extremely helpful, right, when you look at n coin tosses and so on. So we can apply this to more than 2. So I can have a sequence. So xi can be where right, let us say not where, for n independent trials. Of course, they are always independent, I am just saying it, right. Usually you might, we interchangeably use uppercase n and lowercase n, I just wrote it here, right. Let us leave this as n, uppercase. So if you say you have the n independent of the same experiment, obviously the xi's have to be identically distributed, they cannot be, and if it's measuring the same, if each of the xi's measures the same quantity at each trial, obviously you have IID. In this case you can talk of the joint PMF of all of them, right. So I can have a vector of xi, I have a vector of random variables xi, I also have a vector of observations, right. So what is the most important equality we have here? For IID case, that is when, or for this probability, let me write this like this, x1 is some x1 dot dot dot, this is a joint probability. In fact, this is a joint PMF of n this is the joint PMF of n random variables, and I should put, so x1 is x1 through xn, they are some random vector that you pick as possible values, right, that the whole vector, the random vector x can take. So what is this going to be equal to? This is going to be, how is this going to be? What is it going to be equal to? It's the product of what? So you put a pi notation here, pi I equal to 1 to n of what? Well, I actually, IID is not really required, ID is what is really required, but this situation occurs quite a bit in the IID case. There is nothing wrong in writing IID, but what we are really right using here is just the independence basically. You have n independent random variables, most commonly found in, right, the case of n trials, in which case this. So if each of them is a Bernoulli random variable, for example measuring the or indicating the success or failure. So in that case this small x1 through xn would be any arbitrary n tuple or an n vector, right, with zeros and ones, right. And the probability of observing that, which we have already done earlier without calling it a random vector or anything like that, right, we just said 2 heads before 3 tails and so on. Now we are just saying what is the probability of observing the of 1 0 1 0 1 1 1 whatever. So you take it as a right, it is going to be essentially nothing but the product of the individual probabilities, but this is just a formal way of writing this, and obviously it extends to more than Bernoulli. This condition applies to any collection of independent random variables xi. You can have die rolls, whatever. Right. So, and the other important point is that if you know that all n, this is a collection of n independent random variables, any sub collection has to be also independent. So, given n independent random variables, not necessarily IID, or when I say is independent, I mean it consists of any sub collection also contains independent random variables, any and every sub collection. The point is any.